output different file. You have all the file in with this format can be accepted by this Ansys. I use IGS. This is a very common, very normal method to give a geometry model. Okay, that's the, if you know the FE theory, this is like a copyright. You accept this assumption. Okay, accept it. I make use of the model provided in this Ansys. I did not build CAD model myself. Okay, this model is here is C drive program files, and here's Ansys CC website of Ansys. This one, Ansys is here. Here's the date. Here's the models. You see different model. IGS, all this model here. For example, I open the first one. Okay, that's it. Here's the geometric model. But this obviously can be meshed with pet element. That's not good example for this assignment. So I'm going to close this one. I'm going to close this one. Yes, close it. I'm going to input another one from here. List, not list, input files in this format. Okay, accept it. And I'm going to use this ledger. Check, accept it. You have a model like this. This is model. This geometric model from AutoCAD or some other files. We build this one. Next, I'm going to mesh it. I'm going to conduct a finite element analysis. So, start from here. Again, I want all the comments based on structural analysis, active or others. This element type. I use solid element. Here's a brick. Each brick element, solid element, has 8 nodes at each corner, not 20. This is too heavy. Okay, accept it. That's it. Then you have to define material. Material like before. Just give Yas modules. Yas module, I just choose one. Okay, that is given memory. Do you have a real constant? Do you have section number, something like for this kind of solid brick element? No. Depends on the mesh. Depends on the mesh. Okay. You fine mesh, small element. Large mesh, coarse mesh, large element. Yes. And I'm going to mesh it. Mesh it. Here the mesh. No size control. I let the software to mesh it. Oh, yes, I can mesh here, but mesh. Volume. Okay, here, from here, same thing. Volume. I'm going to mesh it. Mesh it. Okay, that's it. Use this kind of element. Head is not good at this compared to this one. Okay, I'm going to mesh all volume. Okay, before meshing, the software check if I mesh this way, the quality of the element good or bad. For example, for the plate element or shell element, if the shell element like this, you to use this too. So I accept it. Of course, the result is not as good as this is the shape testing. Okay. Violate the shape warning limits. Accept it. Just accept it. You see the mesh. Close this one. Use brick element, mesh this model. I don't know how to make use of this part. Because next I have to constrain it. I have to apply loading on it, right? So I assume constraint applied here. Constraint applied here. Applied inner side. And I have another hole here. I apply pressure at this position and see the default stiffness and the strength, okay? But it depends how to make use of this part in system, and you apply corresponding loading constant. But I have no idea how to make use of this part. So I just give a constraint and like that. Okay. This is I'm going to restrict by apply structural displacement on area. Okay, because if you plot area, you find this is the geometric model. But it was built somewhere, not here. Okay, here, and you can plot lines as well. Okay, return back to the finite element model. I'm going to apply the constraint. Constraint, I select inner side. This one. Okay. This is the outside. You see that? The bottom part is inner side. That is outside. Okay, anyway, constraint, sum, and sum. I constrain all degree of freedoms on this selected circle area. Constraint, you see this thing. And next, I'm going to apply pressure instead of the force pressure on area inner area. Okay, that's good. That's just it. And the pressure is along the normal direction. Always there. This is 100 whatever unit. In my mind, I have the unit for this 100, but here, just.
So when you say it's always in the normal direction, so for like any like circular section, whenever you
Whatever,
that
always
section,
along normal.
it's always gonna be normal.
That's pressure.
I'm sorry.
Here is you have the finite element model built next solid. See, give a warning. This warning, that is the file. In this model, you have folder DB file, DB file, and other file, .log file that gives the comment you input to this model. You also have an error model. This error model gives you information which element don't pass the check. All this information contained in that file. You can check that file, find okay where to need modification to improve the quality. Here, I accept this bad element. Of course, this will affect accuracy of the result. It's not the result instantaneous. It takes 1 second because the size of the model. Okay. This is end of the second stage. Post-process, pre-process, solver, and next post-process. Post-process is here. I can plot results, let's say. Plot deformation. Here's the pressure. Here's you see here's constraint. Here's the deformed and undeformed part. You see the difference of these two. Then it shows you the before application and constraint, the shape of the part and its position, and after applying this constraint and loading, here's the deformed part. Can I give a volume stress distribution? Yes, sure. Well, here's the counterplot. The node solution. I want show stress, the distortion energy. Okay, here's stress distribution. This part is stress-free. Why this part stress-free? Because you constrain this part here and the loading over there. This is the loaded part. The stress elsewhere very, very slow. Very, very low. You see that? And you can save it and show other information as well. Strain energy density, and the deformation along specified direction. That's your responsibility because this is a post-process. You show the result. Okay? It's easy. And this function extended the application of this software. You can work in group.